Hello again, everybody. This is Dr. Richard Smith, chairman of the Foundation for the Study of Cycles, and I am back with fellow board member and science director Ray Tomes. Ray, great to see you again.
Hi, Richard. Nice to get together again.
And we are starting our next segment in exploring your work, Ray, in harmonics theory that you've been working on for about 6 decades now, by my estimation.
Yeah.
And I think our first couple of presentations have been well received. I'm very happy about that. We've gotten a lot of views and a lot of interest on it. And I'd like to start today by just kind of reviewing briefly what we've covered so far, and then getting into some new ground. How about it?
Yep, let's do it.
All right. So let me share my screen here. And we'll get started. So I wanted to actually take a step back here, Ray, and kind of go back to the beginning in a way. We didn't really get into this when we started the series, but I think that some of this motivational material is very important for people to understand, why you've undertaken this work, why it's so important to you, and why you think it's so important to the world. So why don't you read this for us and share your thoughts here?
Yeah. So this is Edwin Dewey from 1967. I didn't discover Dewey's work until the late, about 89, by which time I'd been walking in some of his footsteps without knowing it. And this is what he said: insofar as cycles are meaningful, all science that has been developed in the absence of cycles knowledge is inadequate and partial. Thus, if cyclic forces are real, any theory of economics or sociology or history or medicine or climatology that ignores non-chance rhythms is manifestly incomplete, as medicine was before the discovery of germs. Now, there's a sad thing to say about this, and that is that with very few small exceptions, that advice that he gave has largely been ignored. So people are still doing the climate, particularly in this time, that's very important with the fears about that. People are not looking at the past cycles. Yes, they know about the Ice Age cycles, they know about those, but they're not looking at these very long cycles. So the ones that are in geology, that 586 million year, and half of that and a quarter of that, they show up in the records of carbon dioxide and temperatures over the last 600 million years very clearly. And while they know we've been going in and out of ice ages, and theoretically we're due to go into another one, it's very important to work out where we are in that big long cycle, because I think we've finished the ice ages now, and we're actually going to be heading up to much higher temperatures over the next 50 million years. Now, that's a long period, and you might say we don't need to worry too much about that. But it may be that the big increase in temperatures that are happening now are because of that, and they're nothing to do with the human-made carbon dioxide. They're related to it, but in fact, the temperature rises occur. All the studies that have been done show temperature rises precede carbon dioxide rises. So that's something to be for people to think about.
But I think this also has implications, Ray, for cycles on our, within our lifetimes too, right? I mean, I hear people talking about cycles all the time today. It seems like every other word I hear is cycle this or cycle that. I was just at an economics conference. Ray Dalio is talking about the big debt cycle. Neil Howe is talking about the fourth turning and the generational cycle. Everybody's talking about cycles, and yet there is not any science of cycles today.
Yeah. So Dewey was one of the two in the West. He was the leading one. There were other people around like Wheeler, but Dewey was the man who put it together. Yeah. And is it worth mentioning that before Dewey, there was a conference of cycles at Muttermack in the 1920s. And Dewey, after he came out of university with very high honours in economics, he was asked by the then president, why did this 1929 share crash happen? And his answer was, he interviewed 100 economists and he got 100 different answers. And he said, I think that I know which one's right. It's the one who said, Dewey, Edward, we really don't know. And then someone else gave him advice, don't try to work out why it happens, try to work out what happens. And he said that was very good advice. He looked at what had happened leading up to 1929, and he had found that there were cycles and things. And when he projected them forwards, all the cycles turned down at once. The different period cycles all came together. Bang, you get that crash. Now, I didn't know about him doing that. In 1986, I was doing the same sort of thing, and I was working out the cycles. And when I projected them forward, it said there's going to be a crash in 1987. And I got September as the time. It was actually October, but it was near enough. Mm-hmm. And later on, when I found Dewey's, a couple of years after that, I found Dewey, and I started reading his stuff. And what happens in 1967 or so, when he was doing that work, which you mentioned there, he published the stock market cycles, right? So he had the phase and amplitude of each one in period. And when I put all those together, they predicted the 1987 share crash as well, from 20 years before. So it's pretty amazing.
That is pretty amazing.
Yeah. So,
all right. So how about this? This is the second quote.
So while this was happening in the West, while Dewey was in the West, in Russia, it was Chizevsky. There were some other Russian ones as well. We know about Kondratiev. Excuse me. There. So Chizevsky said, life is a phenomenon. Its production is due to the influence of the dynamics of the cosmos on a passive subject. It lives due to the dynamics. Each oscillation of organic pulsation is coordinated with the cosmic heart and a grandiose whole of nebulas, stars, the sun, and the planets. Now, it sounds a little bit new agey, but in fact, although it's very poetic, it's a very accurate scientific statement as well. He based this on huge amount of analysis in all the different disciplines of cycles. Now, this wasn't popular in Russia at that time. Kondratiev got into trouble with him for saying that this cycle happened, something in the economy happened due to cycles, because at the time you were only allowed to say everything that happens in the economy is due to the struggle of the working class. And the fact that that might have come in cycles as well, that didn't occur to them. So anyway, Chizevsky was a bit worried about that.
In Russia, and over here we say everything is due to the work of the central banks.
Yes, yeah, that's right. Yeah,
the working class and the central banks. You know, we all have our gods that we pray down, that we bow down to, right? In our cultures.
Yeah, that's right. So, what the particular bit I like about this is the bit about the influence of the dynamics of the cosmos on a passive subject.
What does that mean to you, Ray?
Well, we're the passive subject. Well, everything is a passive subject. Everything that's happening on Earth. Now, the ancient Hindus had the same idea, so it's not absolutely new, but Chizevsky says it so beautifully. And we like to think that we've got this free will and this ability to do that, and we're in control of everything, and everything that happens is due to humans. It's not. The universe is doing its thing. Our thoughts that we're doing it and all of that's part of what happens. You know, it's just part of what happens. And this thing about the nebulas, the stars, the sun, the planets, all of those, I can show scientifically all of that very accurately. I've been down a similar path. I didn't know about Chizevsky till after I found out about Dewey. I'd come to similar conclusions to that. My feeling is that Dewey was a little bit reluctant to come to the belief that it was all coming from the cosmos, because it sounded a bit new agey or a bit astrological and all of that. And
he conflicts with the narrative of control that we have in the West.
That's right. Yeah. So, but Dewey did come to that conclusion in the end, because when they started looking at cycles beyond the Earth, they had the same period. So, unless we were influencing the whole cosmos, the whole cosmos was influencing us. So he did come to that conclusion, but he didn't want to stress that because he wanted people to study it and do it. Chizevsky didn't seem to be quite so worried about that. In my own case,
Yeah, so let's go
um,
to your
yeah,
summary here.
well, before we get to that one, in my
Okay.
own case, when I was 42 years old, which was 1989, um, I'd been doing some cycles for a while, as you mentioned, and at that stage, excuse me again, the I was trying to use them to forecast. We ran a fund doing futures trading and so on, and we were doing work. I was doing work on that, but all of this other stuff that mentioned by Dewey and Chizevsky was so interesting, and I didn't know about them yet. I decided I wanted to retire. I did. I just found out about them. I decided I wanted to retire and just study cycles, and I'd had enough money to retire because I don't have expensive tastes in living or anything. And so in 1989 I retired. So it's been a long time since then. Um, and I did a lot of work in those early 90s and late 80s and early 90s. I found out about the Cycles Foundation and went in 1989 to talk there and gave my first talk. And since then, I've done talks all over the world, everywhere, on this stuff on many occasions. So yeah, and so let's go here to that. To Tomes's best quote. First of all, I started with a complicated diagram of how everything, like the moon affected the Earth, and the planets affected the sun, affected the Earth, and how the climate and all of those things work their way through to commodities. And then I started tracing up the longer cycles. So like the cycles that Dewey and I had, then I started going to longer ones and working out there's got to be longer ones there. And I got up to 4,600 years. And I think that's about where I was at when I did my first talk at the Cycles Foundation. And then I sort of half jokingly said at the end of that one, what's the longer cycle? Who knows? Perhaps it's the cycle of the universe. And then I started to take that seriously. So the conclusion I came to was the universe consists of a standing wave, which develops harmonically related waves, and each of these does the same. Now, the first two lines, the middle line, the standing wave develops harmonically related waves. In any nonlinear system, that happens. We know that. You pluck a guitar string, play a violin string, it has all these harmonics. The idea that the universe is one of those is my idea, but I think other people have somewhat understood that at distant times in the past, and each of these does the same. Now, that's the important part, because in the past, people have tried to calculate. I've seen a lot of people that do the musical scale, and they understand the power of two, and they understand these musical relationships that I found, but they try to do it with all powers of two, going all the way up to the very long cycles, and it doesn't work. Now, it almost works. When I started doing it, if we go from Dewey's 35.5 years, or my 35.6, and we go up and double it, we get 71, 142, 280 something, 570, 1150, and we get to 2,300 and 4,600 years. So it looks like that's happening, and it's cascading all the way down. But as I got more accurate data, it turned out that the ratio between some of those ones a long way apart should have been 64, but it wasn't. And the value I got when I got more accurate data was 65.05. And the 0.05 was more than the uncertainty. And so I realized it was actually 65. And some of the cycles that were longer, like Dewey had a 2.22 and a 4.44. If you multiply those by 5, you get 11.1 and 22.2, and we know they exist in the sun. So the 5 ratio had to be there. So then I realized, so at that stage, I'd done 2 years of work with a formula that was slightly different, and it gave all these powers of 2 as the dominant thing. So I threw that part out. Excuse me again. It's the case that too many people, once they get an idea, they get stuck on it. In true science, we have to separate our egos from the ideas that we're testing and test them ourselves. I didn't have other people doing it for me. The only person was Pete Brown, did the calculations that I'd done. And he proved that for the first up to so far, he totally exactly agreed with me, and he was prepared to believe the rest. So then I then got this correct formula, which is the calculations we did last time, and that it works. it works correctly then, and you get that ratio of 5 and 13 in the thing, which were giving the longer cycles and linked up to the longer cycles. Now, that was a little bit of a surprise because I didn't expect that 13 there. And there was an 11 further up in the ratios of cycles between the mass extinction cycle and the very long geological cycle. There's a very clear ratio of 11. And so...
Can we let's just briefly review those charts so people can see what we're talking about, you know, and then we can start to move forward.
So this is
Does that work for you?
One thing I wanted to mention on that one before we go.
On which one?
This one we're on.
Okay.
That, a one-dimensional thing like a guitar string or whatever, you get harmonics, but you don't get harmonics of harmonics. And that's the important thing. That's my contribution to this thing is the harmonics of harmonics. And that only happens when you're in more than one dimension. In a three-dimensional wave, that can happen. I think I mentioned that before, but it pays to stress that. That's important. Carry on.
And that's probably where you get the 5s and the 11s and the 13s, right?
Yeah. Yeah.
Okay. Very good. All right. So just very briefly, high level, these were the first cycles that you discovered in your own work.
Yeah.
Doing a factor analysis of economic data from New Zealand.
Yes. And later I realized that those 4 were harmonics of 35.6 years.
Right.
And that they are, in fact, divided by 4, 5, 6, 8, which is a major chord in music.
Exactly. And then you connected your work here, right, with the Dewey's common cycle periods in years where you had the 5.9.
Yeah. So like the 4.44 and the 4.45 agree very well.
Yeah.
5.92 and the 5. Now, Dewey didn't have in that table 7.15 because that's the 5 division. The others are all proportion of 2 and 3. Right. But in his common cycles, he did have a bunch at 7.15 years, so it was known. I think his one was about 7.12 years. So it was good agreement. And he had 35.5 years, which agreed with my 35.6 multiple. So, and 53.3, I knew there was a Kondratiev cycle and that it was about that period. So, so when I found this, I went, yes. First of all, there was a little bit of disappointment that I didn't find it first. And I said, get over it, Ray. This is confirmation that he's using different cycles. He's using different data, different country, and different period of time, and he's finding the same thing. So it's quite clearly a phenomenon that exists over the whole world over a long period of time. And in fact, when we start to do look at the planets, when I did an analysis of the synodic periods of all the outer planets, or all the combinations of the 4 outer planets that you can make of their frequencies, when you analyze that, you find 4 periods that pop up over and over again, and they are very close to 8.88, 17.75, and 35.5 years. So that shows they exist in the solar system, and a lot of the other cycles turn up beyond the solar system as well. So this supports Jaszewski's claim and Dewey's understanding that these are universal things; they're not just on the Earth.
Right. And basically Dewey arrived at 17.75 as being kind of a central cycle. And then he multiplied times 2 up to the left and times 3 up to the right and divided by 3 down to the left and divided by 2 down to the right. And this ended up producing most of the cycles that he had observed across different phenomena.
Yeah. And once you start to put the ratio of 5 and 7 in, you can link that also to the 40.68 month cycle, which is the most commonly reported one, of course, because it's in the stock market. But at this stage, I hadn't found any link to the 9.6 year cycle that's found in the Canadian links and in other things, which is one of the in the Matamak conference in the 1920s, that was one of the major ones they had. So it's very important that when we do this longest cycle and calculate the harmonics, we do pick that one up. It predicts that that's there, even though we didn't put it in, which is a good confirmation.
Got it. So then you started to gather as many cycles as you could. And
now
group them, and we covered this in one of
Yeah,
our
now there's the
earlier
other version of that.
conversations.
That's
So
just the text version of that is probably the one that we should look at first.
yes. So let's see. We decided that was number 860, if I recall. So let me pull that up. 640. We've got a lot to cover here, Ray.
That's why it's going to take a few months.
There's 805. All right, we're getting close. 880, 870, 860.
Yeah.
Okay.
Now,
So
I'm not absolutely
a catalog, or a list.
It's a list.
Of
it's
the
not a complete
cycles
list.
that were in that other.
Yeah, it relates to the other one, but this was an earlier version of that, and it's representative of the cycles, especially in the range of a few years. I haven't listed them all. There's a lot of other ones there as Dewey listed, and Dewey's table should be taken in preference to this for all of that. But it does include some shorter ones in the astronomical area, the 155-day cycle, as it's called, and 77-day cycle, and the long geological mass extinctions and other ones. And so this was the basic data that I fed into my program, which I wrote to try to compare the known cycles as observed to the predictions of the harmonics theory and find out what is the fundamental cycle of the universe.
Mm-hmm. So this is the type of data that generated this table.
Yeah, yeah.
And which is really a catalog of all the common cycles that have been found by Dewey, yourself, and others.
Yeah.
Across different disciplines.
Yeah. That's some of the ones. That just shows how clear,
just a different way of looking at it. But again, this is just cataloging common cycles that have been found and how frequently they've occurred.
Yeah, and I think the important thing about this one is you can see how much the common cycles really stand out compared to the ones that aren't found in between them. And so this is, people say, oh, it's just random numbers or it's just coincidence and all that. And I say, yeah, what do you think is coincidence? I've got some more for you. Because, it's a very clear pattern to anyone who looks at it thoroughly,
And again, this is all just the data, right? This isn't the theory about how these, what's generating these cycles, what's the structure behind the cycles. This is just the data, the raw data.
Yeah.
Okay. And then you started to develop harmonics theory as an answer to the question of what's generating these cycles, how, what is the phenomena or the structure that is leading to these cycles repeating over and over again and occurring at different frequencies.
Mm-hmm.
Okay. So harmonics theory, let's see, where do we begin? You want to just briefly go over this one?
Well, this is how I did the calculation, not the first time, but the second time. The first time it didn't work out quite right. In this, so what the harmonics theory says is the universe consists of a standing wave that has a frequency, right? So we don't know what the frequency is, but whatever frequency it is, it develops harmonics. So that develops frequencies 2, 3, 4, 5, 6. They're all harmonics, all of those from it. And then each of these does the same. So we now take each of those, number 2, and we feed it in, and we get 4, 6, 8, 10, 12, 14, etc. And we do the same with 3. We get 6, 9, 12, 15, etc. And we do it with 4. But now I've done something different here because 4 occurred 2 ways. So at the bottom, I'm totaling these up as soon as we can do them. I total it up, and there's 4's twice as strong as the other. So when we feed it in twice. And so when we get 8,
and that's because there's 2 different ways of making
4
that number.
Yeah, directly from 1 to 4 or by 2 times 2. And when we get to 8, there's 4 ways. And when we get to 12, there's 8 ways. There's just go straight to 12, go 2 times 6, go 3 times 4, goes 4 times 3, goes 2 times 2 times 3, go 6 times 2, go 2 times 3 times 2, goes
12 can be created 8 different ways from these standing waves.
Yeah, so we've now got that calculation now. So that shows the essence of the calculation of the harmonics theory. It's very simple. You can program a computer to do it, and you can do it. you can do it by hand up to 100, which is what we've got there. And when you do that, you'll see in the next couple of ones how that gives music. So 48, 60, 72, 96. If we divide them by 12 is 4, 5, 6, 8, which is exactly the proportions of the original cycles I found in the New Zealand economy. And then when I did the wheat prices, I found these other ones, and they're exactly the musical scale. If we take the white notes on the piano plus 2, the E flat and B flat, those are the strong ones that come out. And those are the exact frequencies of what's called the just intonation scale. And so those are the strong ones. But you'll see there are some others further down ones here as well, which, you know, they may pop up occasionally.
Okay, and just to go back briefly, so this is, you know, done by hand, basically up to 100, shows which are the strongest, which have the most combined ways of creating that harmonic, essentially, right?
Yeah, and then to get from this one to the next one,
dividing it.
I'm dividing the number of ways that it can be made by the harmonic number, because as we, when energy is lost to harmonics, which we described, that's how they form. If you pluck a guitar string, you'll get quite a strong second harmonic, a bit weaker for the third, and so on, all the way down. And by the time we get to 96th harmonic, it's very, very weak. And so we're dividing it by the harmonic number to recognize the diminishing power. Now,
so if we take, harmonic series, 48, just as an example here from the previous slide, it has 48 instances. And so when you divide 48, you know, by 48, you get 1.
You get 1, right? Yes.
And so that basically is how all of these numbers were created.
Calculate,
and it kind of normalizes things.
That's right. Now, when I do the very large numbers, dividing by the harmonic number is not enough, because they go up faster than that. Now, it works out that the Harmonics theory will work exactly correctly if the energy drops off as the harmonic number, or the harmonic squared, or any power of the harmonic number. It doesn't matter. They all give equivalent results.
Okay.
And so when we do these higher ones, I divide, on my webpage, I show a calculation of how I deduced the correct way to, that it drops off with higher power. It's not terribly important. It only shows whether this thing goes upwards or downwards a little bit as you go across. But the local peaks remain exactly the same. And so we see there's a wobbly top to this. There's sort of a wave-like structure in the peaks.
Yes, and you actually have some diagrams that we should show here.
Yeah, that's right.
You show some of the structure within this chart. So let me just take a minute and find those charts and bring them up for everybody. Give me just 1 second. Okay, Ray, I found them. I remember last time I kind of sketched these out with my drawing cursor, but this is some of the structure.
I had too many diagrams. We couldn't find them all.
So go ahead and explain it to us.
Yeah. So this is, I call these families of cycles because like Dewey showed, there's lots of ones with ratios of 2. If we start from harmonic 1, we can see 2, 4, 8, 16, 32. I put a line through those. Right. And we can see that they originally rise up and then they fall down and get weaker and weaker. But when we multiply by 1 ratio of 3, we start at 3, we go 3, 6, 12, 24, 48, 96. We rise up again and get a higher peak there. So in Dewey's table, a power of 2 was down 1 diagonal. This one is the next diagonal across from that. And if we move across again, you get the yellow one. Now, I'm sorry, yellow doesn't show too well on here. But it goes goes up through those ones, 144, 288, and so on. And then by another ratio of 3 and so on.
3 to the 3rd, right?
Yeah.
And then 2 to the n times 3 to the 4th.
So you can see there that in any one part of it, you're getting there's a range of them that are strong. And Dewey did a Pythagoras's lambda in his one. When I gave my talk in Russia in the 90s, There was a young woman there, and unfortunately, I didn't get contact details with her. She would be a very good person to have in the Cycles Foundation. And she had understood that you could keep going in each direction with Dewey's one, but that you didn't. And she wanted to know why. And when I showed something like this, she said, that's why. So that's how it
stopped. Other
stopped.
structures in here as well.
Yeah, yeah. So now this one, we saw that when we just added powers of 3, it gradually faded off. So now we start doing a power of 5, and that starts coming up until we get with one, we get 2 to the n 3 squared times 5. So with 2 powers of 3, we get that big one, yeah. And
so
then
the
the
first
next
one actually is back here, 2 to the n times 3 times 5.
No, further back. That one way down the bottom left, that one, yeah.
Way down here.
Yeah, so it's quite weak to start with, but it gradually comes up. And then again, that gradually fades out as well. We have to go a bit further before that fades out. But that peak there around 17,280 and 3560, 34,560, that's the biggest local peak for a long time, right? And then a power 7 comes in, another power 5, and we eventually get the other ones. Now, we need to look at it a different way to show all of those. This is the detail, and it shows why in some ranges you get sort of not so clear cycles, because often you get ones that have got nearly equal size that are right next to each other, and they interfere a bit with each other, or they get modulations. And so we do find a lot of modulated cycles. That's all.
Found that, that the cycles at these peaks, 12, 24, 48, 14.
They're the clearer ones, yeah.
That these are often the strongest cycles that are found.
Absolutely, yeah. The 2880 of the Hubble scale gives a very clear structure, which we'll get to later of galaxy spacings and stuff. So. Galactic cluster spacing, sorry.
Again, just to emphasize for everybody, like what we're looking at here now is theory.
Yeah, absolutely. Right? This is just all derived from that one simple statement. Yeah, that's right.
Pure theory that's lining up with observation.
Yeah.
And also making predictions.
Yes, absolutely. Yeah.
And filling gaps that that Dewey had not filled.
Yeah, because he didn't know where to stop. Like he had 5.92 years. He didn't have 11.84. There's a very clear cycle there that exists in many things, and I think it's in his list. But if you kept going, you don't know where to stop. You could keep on putting those in forever, but there is a reason to stop, and it's when these things get weaker. Get weaker and weaker.
There was one more new chart that you wanted to share. I think
2 before that one. Yeah, this is another way of looking at what's happening to help understand it.
So what are we looking
as I
at
said,
here?
every wave is losing energy to its harmonics. In this case, I've structured it just showing the ratios of 2 and 3 only. Now, so the number 1 wave's losing energy to the 2, to the 3, and to the 4, and to the 6. It's also losing to 5 and 7 and other ones, but they don't play any part for a while. And number 2 is losing energy to 4 and 6 and 12 and 8 and so on. And so you can see energy can only flow to the right or downwards or diagonally downwards. It can't flow back upwards. So it only goes to multiples of the thing. Okay. So what happens is, as it flows downwards, the one that's going out to the right gradually gets weaker and weaker. That's why the 1, 2, 4, 8, 16 gets weaker, and the other one starts picking up. And when we get to 12, 24, 48, they are the dominant ones. But then that flows down, and we get 144 and 288 and so on. So that shows you why those ones become strong with the flow of energy and the loss of energy to other things. Now, when we go beyond that, we would have to put in a ratio of 5 as well, which would mean going to a third dimension, and I'm not trying to do that. It's just an alternative way of understanding why, as you go up just in powers of 2, they get weaker, and you have to put these other ones in the power of 3 every so often.
Got it. Okay. So we've been studying this one, and then this is just taking it further out in calculations.
Yeah. So each time a new model, I originally did this on a 286 an AT computer, right? And as a new models came
I
out,
haven't heard that
I
one
do it a
for a
bit
while.
further.
The
Yeah,
286.
that's right. I did it
I
to 10
remember
to
all
the
those
20.
processors, the 386 and the
Yeah, 486,
486.
586. The last one I did was a 586. I don't know what they're up to numbered now. They're about probably up to 1286 by now.
At least. Yeah.
They don't call it that. But this one had, you can see that the calculation conks out towards the end there. So it gets up to about 50 or so, okay, 40 something, 50. And so though this data here, all the reasonably strong ones, I've put into a spreadsheet and saved them on my website. We can do a link to that if people want to download it. And I can tell you some more things you can do with that. But the basic idea is,
so yes, something like this, right?
Yes, that's right. Now, when you download it, it doesn't have the two right-hand columns because you just have to put in the one figure for the years, and then you do it divided by the harmonic number all the way down, and that gives you all those numbers. And when you go further down that, you will see cycles and the geological cycles and so on, and all of that. But we really need to do first now the calculation of matching that up, matching up the harmonics calculations against the observed cycles. So we have the observed common cycles, and that that one gives. So that one's showing how that matches, how that shows that the very strongest expected cycles agree with the geological cycles, the mass extinction.
Again, this is the theory over here. These are the calculations from harmonic theory, and then these are some of the observed cycles. Yeah, and so it's important to understand that the reason there's mass extinctions, people have got all sorts of theories about another planet whizzing through the solar system or ducking through the plane of the Milky Way. We may do those things may happen, but it's driven by these universal harmonics, massive energy. When you put, I mean, I noticed like these cycles that have been observed, you didn't just randomly pick them out and say, oh, this one matches, this one matches. These all have a strength, I presume this is.
This is the strength here,
above 1, and they're lining up with observed phenomena from the literature. So what is this strength metric? Is that just going back to,
well, originally I was doing
being above
it's
1?
It's more or less doing that, but I divide by a power of h, which gradually changes as you go further up because the rate at which they grow goes up faster and faster.
So something like above 1 on this chart?
Okay. On my webpage I have got that calculation. I worked out I made a formula that approximates to the general sweep of the whole thing. So it's not trying to get, it doesn't follow the little local wobbles, right? It just follows the huge sweep of the thing. So it tells you which are the strong harmonics in any range if they're relatively above that. Got it.
And then these are some other cycles.
Yeah. So this is in the human range now. So we can see, so like that 23.7, that 22 years, the sunspot cycle, that's strong. The 23.7 is not often mentioned. And one of the reasons is when people have a bit of data, they assume it's a 22-year cycle. But that 23.7-year cycle does occur as a modulation of the 40.68-month cycle in the stock market. And it gets it fixed the phase and the amplitude of that. So these other ones do occur. 11.86 years. Now this is one important thing. 11.8622 is the period of Jupiter around the Sun, right? And I always consider that before I did this as the most accurate one that we can work all the other ratios off in those shorter periods. So the fact that it agrees to 6 digits is very good because the calculation of this I based off Afanasiev's 586.24 million year cycle. And the fact that it agrees to 6 digits by the time you've gone through all those ratios, it's a good confirmation of it going on. And one of the other things here is, where is it?
This cycle generated through your harmonics math agrees with the orbit of Jupiter to 6 digits?
Yes.
That's remarkable.
Yeah. Now, you don't see the 9.96 year cycle in there. It would have been a little bit lower on that. But when we go to those graphs that have got the time period running horizontally. and the peak sticking up.
This 3.389 is the 40.68 month stock market cycle, right?
That's correct, yeah. And I get 40.67 months from that. And I told that to Richard Mogi. And he said, well, it always comes out as 40.68. And then one day he sent me an email. He said, Ray, I've run it with updated data now, and it gives 40.67 months. We had a good laugh.
Well, that's fantastic, because that is actually showing theory predicting something that didn't match with the data, and the data then coming around to match the theory.
It matched pretty good. I think they did very well getting to that accuracy.
40.68, I'll take it.
Yeah, that's right.
Fantastic. All right.
Now, I think a little bit further on, you've got, or you can let me do it, the ones with the period running horizontally and the date sticking up and the little triangles, colored triangles marking them.
All right. Let me just find that. Give me just 1 second here. Okay, so I believe that I found the other slides, Ray. And again, we're looking at how the theory lines up with the observed data.
Yeah.
So this is just another way of looking at it. We had the spreadsheet before. Now we've got a diagram here, and the black lines and the numbers are the predicted cycles from the harmonics theory, correct?
Yep, that's right.
And then now you've got some red and purple triangles on here.
Yeah. So those red triangles, if you take Dewey's table, he had 17.75 years, right? So you'll see that red triangle next to 17.79. And I've plotted it a teensy bit right. I've plotted all of these in exactly the correct place. And you can see that it matches
slightly to the right of 17.79.
Yeah, that's
the
right.
center of the triangle. So it's 17.75. So lines up pretty close, but not perfect.
And then the next one you get at 35.586, you get there. And so it's slightly to the right again. But remember, I had 35.6, so mine would be a teensy bit to the left. And you can see the 71 year side, 71 there, and 142. And those are some of the other ones. There's the Kondratiev one down there. It's not predicted to be quite so strong.
Kondratiev here at
that one there, yeah. So and a number of the other ones, the 4.448, 5.93,
5.9,
8.896. So those ones. Now the purple ones are something different. The purple ones are 9.638. That one there, that purple one there, was not part of Dewey's table. But now, when you look that one up for in Dewey's things that they found that in, they found that in quite a few things, the Canadian links, but a lot of other stuff as well. And there's two numbers given there.
Was that the Canadian links cycle from the Matamek conference? Matamek?
That's right.
Matamek? Okay.
Yeah. And so they give 9.6 years as one figure and 9 2/3 years, about half each. So we could say the correct figures somewhere between 9.6 and 9.666. So we could say 9.633 is about their average, right?
That
plus or minus a little bit, and we get 9.638. So that's now that one was not that cycle was not put into the calculation for the longest cycle, and yet here it is coming out. And you could say, well, okay, that's not the biggest one. There's 9.885 there, but that one turns up as well. In the sunspot cycle, 9.9 years. And so, and these other ones,
you've got
11.01 years turns up in the sunspot cycle as well. Yep, that's the 40-month cycle, and it gets that real accurate.
And then why do you have this 11.86 highlighted?
Because that's Jupiter's period correct to 6 digits. So and I didn't put that in. I used the figure that Afanasiev said for the longest geological cycle, which he said is 586.23852, plus or minus 2 in that last digit. Yeah, I don't know how he got that accurate, but I can't say it's not right.
How's that connected to 11.86?
By ratios, all the ratios are 2 and 3, and the other ones that occur along the way down there get you to there exactly. Yeah.
All right. So that then if we go to a few shorter time
Yeah.
frames, so these are
Now the
3
blue
years
ones,
and less.
yeah, the blue ones there are ones that are found in solar things, shorter term solar ones. They find us in about 4 or 5 different variables on the sun. So those ones, they all come out strongly on here. That 0.07 year one is 25.8 days. I think, yes, that's right. That's the rotation period of the sun. And these other ones,
0.07, this one?
yep, yes.
Or this one?
No, 0.07. Next, down
0.07,
the
sorry,
second
down
line.
here.
Yeah,
Gotcha.
yeah. And all of these things turn up. On Cycles Research Institute, there's an article I wrote about all of those ones. The fact, some of the people that observed some of these did notice that they were harmonically related. Although I got in touch with one, they were hard to contact because these were done mostly in the 1980s. I contacted one of the guys and I said, "Oh, you've noticed that they're harmonically related?" "No, I haven't." And so it was I realized it was one of the other guys and that he hadn't noticed that at all. And yet it's pretty obvious. Then these other ones on the red, they're all Dewey's cycles in this table. And you see that, well, I think the 1.97 is, he has a 1.98 year cycle, doesn't he? I think he does. 2.96. I think those are in this table as well. So for some reason, I haven't marked all of them.
Okay. All right. And again, theory versus observed data. Lining up pretty well. Very good. Okay. And then I think that next we wanted to look at this chart.
Yeah. So how did I calculate the longest cycle of the universe? First of all, I thought it was going to be 14 billion years, and the thing worked moderately well for 14 billion years, but there was a problem, and that was that one ratio over the long intervals. I mentioned 5 times 13 being 65, near to 64. In this case, it was 13 times 11, 143 being near to 144. And that, because you haven't necessarily got accurate figures to start with, that one led to some confusion. And then I realized, no, it's longer than that. And so I said, I started at 10 billion years because we knew it was more than that. And I varied a number by a little tiny bit each time, fraction of a percent, a tenth of a percent, I think. And I gradually went upwards. And I measured how well did that fit to that list of cycles that I put in that were known over different ranges. And as you can see, it wiggles up and down, and it finds the odd one where it fits moderately well. Then suddenly you get this big burst of big peaks. Now, why is there multiple? Well, 1.4821824 times 10 to the 23 years is the one that matches very, very well. And we can see that when you go to half of that or double that, it matches quite well, because we know the pattern of cycles when you move by 1 power of 2 doesn't change very much. And so again, by 4 each way, and by 3, and by 4 over 3 and 3 over 2 and stuff, they all match up as well. But it's quite clear that the longest cycle has to be 1.4821824 times 10 to the 23 years. It's a very long time. Now, that number, I'm not the first person to get a period near that. I have to confess. The physicists at one stage had a theory that protons might decay, and they worked out the period of it. Now, I don't know the exact answer they got, but I know that they expressed it in seconds, 10 to the 31, I think it was, around about. And so this is exactly the correct order of magnitude for their proton decay. But after I tell you the second one of these things, it may be that they couldn't find them. They had enough protons to find them, they didn't find them. And it may be because they don't do it randomly, they all do it at once. So this comes to the second one. The Buddha, someone asked him, how long the universe goes. He says, oh, it goes in cycles. The whole universe arises and passes away once, and they didn't have powers of 10 notation then, right? So he said, and in the units of the day, it's been translated into English, it's a hole 7 miles by 7 miles by 7 miles, and you fill it with sesame seeds. And then what you do is you take out 1 sesame seed every 100 years, and you keep doing that. Of course, the Earth's going to pass away before that, but to get the idea of the time, if you do that, I calculated, I said a sesame seed, I reckon that's a millimeter each way roughly. And so I divided a millimeter cubed into the 7 miles cubed, calculated it all out, and I got 1.4 times 10 to the 23 years. So I don't know how the Buddha did it. I know how I did it. But that's what he gave as the time for the arising and passing away of the whole universe. But it keeps on doing that on the cycle.
So
And he gives
I've got some questions here to understand what we're looking at, because I'm not completely clear myself, and I'm sure not everybody else is as well. Would you say, is this what we're looking at here a continuation of these charts here?
Correctly. We're taking that.
Yep. So
and we're comparing that against the list of known cycles.
You know, somewhere in this, 10 to the 18 to 10 to 36, right? Because it's only up to 10 to the 23rd.
Yeah, but we do have some that's shorter. Yes, yeah, we're only using up to about 10 to the about 25th or so. Yes, you're right.
Okay, so you're estimating what is the longest cycle in the universe.
Yeah. And
you are anchoring that off of some of the observed cycles.
Yes.
And then so that list, yeah, go ahead.
That list we had before that we put up, that was a sort of more texty sort of thing with the...
Right, that was way down here. I think it was like 860 or something, this one.
That one, yeah. So my memory's failing me. That may be the exact list I put in. It may, but if not, it was similar to that.
Okay.
That I put in.
So you put in this list.
Yeah.
And then you looked for, which range of cycles matched up the best.
Most closely matched that. Yeah.
And then you arrived at this one cycle of 1.48 times 10 to the 23rd as being
the one that fitted it best.
Cycle that matched all of the other observed cycles.
Exactly.
And it also lined up with the Buddha's aphorism of a sesame
seed
every 100 years in a 7 by 7 by 7.
I don't know how he did it. He was a very clever chap.
Very clever chap. Okay. Do you do anything with this number, Ray?
Yeah. So the physicists, I've never managed to find what was the half-life of, which wouldn't necessarily match to this, but I'd like to know the calculation they do to get to that, because on the Buddha's one, the whole universe, the whole physical universe passes away and then restarts again. So it's like a Big Bang repeat, except it's a much longer period. Another guy I like a lot is Fred Hoyle, and he had a theory which I haven't seen the details of, but it was that there was he called them like small bangs, not quite so big bangs, that repeatedly happen. Now that's consistent with the my calculations, that like when I do those other long cycles, there will be very dramatic events that happen. I think you need to let me, hang on, I'll tell you the number.
Okay.
You might want to pause a moment.
Sure.
Yeah, so what I thought is, what happens if I take all these harmonics that harmonics theory predicts and add them all up? And the answer was slightly surprising. This is the next one here. I've broken this into 12 sections. So this is really one very long graphic, right? I broke it into 12 because 12 is a strong harmonic, and you can see that each line's similar. So when I added all these different sine waves together, well, actually they're cosine waves. When I added them all together, I expect to get something looking a bit like a stock market graph. No, that's not what happens. It makes a horizontal line with a bunch of vertical lines sticking up from it. So waves turn into particles, but they're not all the same. You can see at the end of each line, there's one sticking up. In fact, they're sticking up so far they're hitting the next one. So the 12th harmonic is very strong, appears all throughout. And in the middle, you can see the 24th is strong as well. And then at the quarter and three-quarter, that's the 48th harmonic. And then a third of the way across and 2/3 of the way across, which means you're getting, there's a 36th harmonic. You can see that's quite strong as well. And you can see each of these sections is quite similar. If you got the musicians drumming on this, it would all say, there'd be boom, 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 and boom, 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 and boom, 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 and so on going. But every so often, a little bit something different happens. There'll be one. Let me find one. Okay, in the third row down, a bit to the left, a little bit to the right of where you are now. That one, a bit further. You can see that one's a little bigger than the other ones on there. That's 1/5 of the way through the whole thing, right? Through the entire thing. So that's the fifth harmonic, and those ones will turn up only in occasionally, not all the time. So the whole thing, it's got sorry. It's got a little rhythm going all the time. This is only looking at the universe on the hugest scale. If we keep on zooming in, zooming in, zooming in, we'll find similar patterns of this happening all over the place. And as we go down, instead of just being ratio 12, other ratios come in. So when we get to the solar system, we find that there's a ratio 14 between the outer planets and the inner planets. And in other places, there's other ratios that happen when you get down to the atomic scale. Other ones come in again. So, but the whole thing as it's predicting is that it's
so
that's the structure.
I understood. Sorry, Ray. I understood. This was a segment of this.
Yeah, that's right. Yeah, right? That one was matching this to the observed cycles, right?
Right.
This other one that we were just doing is nothing to do with observation. It's predicting, rather than take the cycles one at a time, it's putting the whole lot together. So this is adding up loads of nodes of harmonics. We don't have to go too far because we'll get smaller than pixels on there. But basically, that's showing that when you add them up, and we see this sort of thing in the stock market, don't we? We see the stock market does dips, and a whole lot of lows come together, and it goes boom, and away it goes again. In commodities, it does the other way around. It goes up, and then it comes down again. And these things happen, and you'll find that they often happen at intervals. So, like when I've looked at some of the commodities, I found you get call it 54-year cycle to make it simple. Kondratiev, you get 27 and you get 18, and those all show up in also 12 years, but they're not perfectly regular. So you can see here, when we go from the middle of that first line to 3/4 and then to the end, they're equal intervals, but 2/3 of the way through that first one, we get another bit, which is there in the other one, but nowhere near as big. So you get patterns of it. Like that. So you're getting multiple rhythms happening at once there.
I really would like to unpack this one more, Ray, but maybe next time.
Yeah.
Because this seems to me a very intriguing chart.
Yeah.
And
there's lots of ways of looking at it.
I really would love to understand better how you created it, because I don't quite get it, but it seems potentially very simple.
I created it. I made, for that whole length there of those 12 sections, I made one cosine wave, which is harmonic 1. Then I made a cosine wave that goes up and down twice, which is harmonic 2, and then 3 and 4, and all the different ones. And for each one, I gave it the amplitude that the Harmonics Theory says that one should have. So it's purely a construction of theory.
Them together?
I just added them all up, and then I printed it out, and I got a surprise because I expected it to have some sort of wavy nature, and it got rather more of a particle nature, hasn't it?
It sure does. And as you go along, what is the horizontal axis, unit here? Is it?
Well, it's a fraction of the universe, if you like. If you take those 12, it's the size of the universe. But something similar happens at many scales. When we'll look at next time, we'll perhaps look at pictures of Jupiter, and you can actually see a number of these harmonics in the cloud patterns of Jupiter. But we start from the bigger scale of the universe and work down. So I think you've got one there of the observation of galaxy clusters. Oh no, do that one first. When we do these cycles, we often get different cycles and different things, and what appears in different things, I think, is largely a factor of a result of which ones has a natural oscillation period. So like it's a singer in the wine glass thing. If you happen to sing a note very near the frequency of the wine glass, it really goes. And so obviously, like the stock market likes cycles around the period 3 or 4 years because a number of those show up. In this case, we're looking at the sun, and this is called the solar magnesium 2 index. It's supposed to show something to do with ultraviolet output of the sun. And so this is a spectral analysis. The big lower graph is showing ones. You can see that there's the ones labeled in blue, 1, 2, 3, 4, 5, 6 down there, are clearly fractions of the solar rotation period. Now, you get different values for the solar rotation period in different graphs because the sun, it doesn't rotate uniformly. As you go further away from the equator, it rotates slower. So sunspot rotation is different to the equatorial rotation. When you go deeper, it rotates at a different rate as well. And so you'll get different things, but it's clearly related to the solar rotation. Now, the little insert graph is the very left-hand part there magnified up. And you can see there, 51.8 days, and in blue, 2, 4, 6, 12, 24. So the periods that are found in there, 156 days, which is 3 times the 51, and then double that is the 321, and double that is the 642. So we're getting gain ratios of 2 and 3 showing up. But this is unique. I've never found any other thing that has that many harmonics related, how the harmonics theory says, between long and short cycles. So we go 24 ratios to get to the 1, and then another 6 to get to the 4.6 days. So we've got a total of 144 in the ratios there, in exactly the sort of manner that we expect from harmonics theory. Now, the lower graph is not unexpected. There are good reasons for those to exist, independent of harmonics theory. But the upper ones, which are strictly called subharmonics, I don't believe there's any good reason for those to exist. And people that have studied those cycles, I mentioned the 154 and related cycles before, and we'll study those in more detail.
158?
55. Yeah, that one's got 156. Most often, my average, 158. My average one, I reckon, is 154.7. But you get slightly different values in different things, but it's clearly there in the peak. So that one's unique in that the sun obviously responds to the universal waves better than most other things do. Now, the one after this, in India, they have this thing called the monsoon, and they get massive rain for about 4 months or so, 5 months, where they get rain like about 5 or 10 times as much as most people get in a year. And so if you analyze it, you'll get a yearly cycle, and you'll get some harmonics of the year, half and quarter and a third and stuff of a year. So that's not so interesting, but if you remove that yearly cycle, if you divide throughout by the average of that cycle, you get something quite different. And I've got a graph of that somewhere, and we'll do that in more detail. But what you'll see here, the green arrows there, green triangles show 75 days, 153 days, 303, 627 days. Again, they are doubling, just as the same in that previous graph. Those cycles exist in the sun. Now, previously, those have been solar cycles. I've not seen those in anything on Earth before. I did this particular analysis on Indian rainfall. So we'll come back to that one in more detail, I think, later.
Quick question, Ray. I'm curious why your charts always move from right to left.
Oh, okay. Because at the bottom, you'll see its frequency.
Okay.
Strictly speaking, when you do cycles analysis, you do it in terms of frequency. How many
times that cycle occurs? Period
is the reciprocal of frequency, so that's why the periods go that way. We're going to get even more confusing. For some reason, climatologists do time from right to left, which I find very confusing. So we'll have to deal with some of those at some point as well. Yeah. And then, now, I think you've got one more here, if I remember. This one, and this was something that we'll cover next time, I think. This was published in a New Scientist in March 1990. Now, they call it mega walls across space. And what happened is there was a joint US-Australian project. They looked up in one direction in space from America and down the other way from Australia, and they just they called it a pencil beam, a very thin beam that they looked at, and they just counted all the galaxies and the red shifts all the way out there as far as they could go. And then they plotted this graph, which was the average of the two of them. And you can see that it's very clearly got regularity in it. They give it now, astronomers use units which are based on their wrong theory. They said they're placed at 128 megaparsecs apart, and times the Hubble constant, which was assumed to be 100 kilometers per second per megaparsec over h naught. These days, h naught, at that stage, h naught is the Hubble constant, was thought to be somewhere between 48 and 96. So they standardized it to 100 so they could calculate megaparsecs. But really, it's now settled down to about 71.2. So that's the correct value to put in. But that's not the point here. The point is that 128 megaparsecs, because that means 12,800 kilometers per second when you wrongly interpret red shifts as velocity. And so you have to undo all the wrong assumptions, and you can get out of this what's really happening. And these regularity of spacings work out if you use the correct Hubble constant, which since then has been proved. At that stage, I said it's around about 71, 72. And since then, that's the average value has closed in on that. And I said you can work out the Hubble constant very accurately. So taking that, when you use that value, those are at 586 million light year spacings. Now, you've heard something like that before. 586 million is Afanasiev's geological cycle. Mm-hmm. So if there's a huge standing wave in the universe, and I say there's a lot of them, and it's got a 586 million light year wavelength, it will produce a pattern like that in galaxies. They form on the nodes of these waves, right? And then the geological cycle says this oscillation is happening of 586 million years. Those two coincide. They're the two aspects, the wavelength and the period of those massive waves. So this is very strong support for my view that the universe is composed of standing waves. We'll do the same thing at other scales. The same thing happens at the scale of galaxies. It happens at the scale of stars. It's very clear. It happens at the scale of planets. It happens at the scale of atoms and subatomic particles.
So were you able to reverse engineer the Hubble constant essentially
yes,
from this data?
Correct. I got a value of, I said originally said it was 71 to 72. Once I got, in the 1990s, when I went to Russia and I got Afanasiev's figure, I came out and I could say, yes, it's 71.2 based on his one. It could be done more accurately if I had the data from this. I've tried to get this data because then I could analyze it and get the period very accurately. They've done a good job of it, but it can be done better because it would give that. So yes, I reverse engineered it in the 1990s. And since then, we've seen it close in on that value there. I tell this to astronomers. I put it in all sorts of places. Everyone totally ignores it.
So what we're looking at here, distance essentially from Earth.
Yep, that's right.
Going out to the right, getting further and further away. And this is kind of like a frequency or a density.
Density of how many galaxies there are. How many
galaxies there are.
Yeah, and you'll see that there's, as well as that main peak going down, you can see some secondary ones as well. And they do have evidence. Now, I mentioned the 586 million year geological cycle. You can find them there, the half year and the quarter of that as well.
Where is the 586 million year cycle on this chart?
Well, this is light years. If you take it as light years, then I haven't got the scale of it there, but you can deduce it from it here.
Okay.
I've done an article on that. It's on Cycles Research website. There might be a video on it as well, I'm not sure.
Again, you started out intrigued about cycles. You came across Dewey's work. You came across Krzyzewski's work. You developed harmonics theory as a way to explain the observed data. Yeah. And over decades now, you've collected more and more observations that all are lining up with the structures predicted from your harmonics theory.
Yeah. And the interpretation that these are standing waves in the universe. Yeah. I think we call them electromagnetic. More recently, I've come to the conclusion.
Go
I
back
used to say
Ray's theory of the universe.
Yeah.
The universe consists of a standing wave which develops harmonically related waves, and each of these does the same.
Yeah.
And one of them is 586 million years.
Yeah.
Where do we go from here, Ray, next time?
Well, I think we can start to look at different parts of that structure. So we had a graphic there that showed that the spacings of things like, if we go from the Hubble scale, we get the scale of galaxies, the scale of stars, the scale of planets, the scale of moons. Then there's two not so obvious one scales that might be there. And then there's the scale of cells, the scale of atoms, the scale of nucleons, and then the scale of what we call quarks and you call quarks. Is the predicted next one. And I could, even when they were first talking about that, I can predict where that scale would be. And that's not the end, there'll be another scale. But I think that in the part of the universe where we are, you can have free neutrons and protons, but you can't have free quarks. But I think that if you go to, say, the core of a galaxy where there's a black hole forming and stuff, and all that stuff's going on, I suspect under those conditions, you can have free quarks, and maybe when you get the biggest galaxy of a huge cluster, at the center of that, there might be even another step. I don't know. That's a possibility.
Okay, but the basic idea is that we're going to apply harmonics theory to different scales of structure.
Yeah, so we go to the galaxies,
large and
we'll
small.
do the stars. People have looked at the galaxies and found those structures.
What's that?
People have found the structure in the galaxies and the galaxy clusters. No one else had looked at it in the stars. I did the star analysis, and it shows that there are regular spacings in the stars, and you'll be surprised by how many light years apart they are.
And then we'll go down into cells and particles.
Yeah, all the way down. Yeah, we'll go all the way. We'll do all of them. We'll do the moons, the human scale. The rock formations.
And we'll see harmonics theory manifesting at all those scales.
We will, yeah.
All right. I look forward to it. Thank you, Ray. It's been great.
Okay. Thanks, Richard.